Hello, welcome to this lecture, number 5 in our course, and the topic today will be on matrix elements between Slater determinants. And this is of general importance, obviously, but it's also something we're going to need when we want to calculate the expectation value of the Hamiltonian when we approximate wave functions by Slater determinants. And this in turn will enable us to minimize this energy, and that is the essence of the Hartree-Fock method. So to keep things as general as we can, we'll consider two different Slater determinants. So let's assume we have a set of single electron orbitals. So they could be phi 1, phi 2, all the way up to some high number here. So just as an example, one Slater determinant could be constructed by simply selecting the lowest number. Let's say we have 10 electrons, so that could be one Slater determinant. But then we might have another one where, say, number 2 is replaced by something different, and this should obviously be one which is not present already. So number 2 might be replaced by number 13. Just some arbitrary example here. The point is that we consider Slater determinants constructed from single electron orbitals that comprise one single set. So what this means is that all of these are in fact eigenstates of some particular single body Hamiltonian. So they are eigenstates of this sort. But we can of course select different states among this set and construct different Slater determinants. The notation we will use is that, so this set here, what I might say is that at some point here I have an orbital that I could call phi I, and in this other one at this point will be phi I prime. Actually they will all, I will give them all primes, but in many cases of course the prime orbital will be the same as the unprimed orbital. But what this simply means is that if I consider phi I prime, this just means that it's the phi I with this I replaced by some other quantum number which we might call I prime. So that's the meaning of the primes. It's simply that we select another entry from this this large set of single body states. And of course these single body states are also orthogonal. So what we can easily say is that phi I and phi I prime is delta I prime. So if the I and I primes are the same, we get a 1, otherwise we get a 0. So they are orthogonal. And we also note that if two identical orbitals enter in both of these Slater determinants, they will be placed at the same position. So it's not like I could have a phi 1 here, and then at some other position over here I would also have phi 1. The point is that if they appear in both of these Slater determinants, they will also be put at the same position. So that is the assumption. And we will consider two different types of operators when we're going to calculate these matrix elements. The first case, A, will be an operator if which is a symmetric sum of single body terms. So it's a sum over all electrons, some F operator acting on electron number I. And the second case will be a sum of two-body terms, G operating on I and J, with the property that this is a symmetric operator. Interchanging I and J should make no difference. So those are the two types of operators we will be looking at. And these are obviously what we will need for the energy. The single body part here is the kinetic energy and the interaction between electrons and nuclei, and the two body operators here are of course the electron interactions. So in order to keep things reasonably simple, I will only look at the two electron case, and I will derive formulas for this case, and then afterwards I will try and argue how we can generalize this to an arbitrary number of electrons. So what this means is that I have one Slater determinant, which is this phi 1, 1, 1, 2, 2, 1, 2, 2. So this is the unprimed state, and then there's the primed one, which of course looks like this. So these are the two state determinants we will be considering. So let's start by seeing how far we can go without assuming anything about the operator other than the fact that it's symmetric. So if I want to compute this matrix element between these two Slater determinants, then I get a factor of 1/2 from normalization. Then I get the first Slater determinant, which I will expand here. So I get a 1, 1, 2, 2, minus 2, 1, 1, 2 here. All of this conjugate, and then my operator, and then the other determinant, which I will keep in its matrix form here. And then of course I have a number of integrations. Let me for brevity write it like this. What this of course means is that here I have to do 3 spatial integrations for electron 1 and 1 spin integration, and the same for electron 2 here. So altogether this is an 8-fold integration in that sense. Now you see that I have, if I expand around this minus here, I have 2 terms. In this second term here, the difference with respect to the first term is that the arguments are interchanged. So here 2 has been replaced by 1, 1 has been replaced by 2. But I'm also going to integrate. So these are just integration variables. So I could again interchange 2 and 1 here just for the sake of the integration. Then of course I would also have to do it here in this later determinant. So I would have to interchange 1 and 2. So that, as you can see, amounts to switching columns in my matrix. And you know that switching columns implies a sign change. So when I do this interchange here, this will cancel that sign change here. And remember that by assumption my operator here is symmetric. So if when I interchange 1 and 2 in the operator, that should have no effect. But the point is that upon interchanging 1 and 2 here in the second term, I will get a term which is precisely the same as what I get from the first term, and that of course will then cancel my factor of 1/2. So doing this, I will just retain the first term, which goes like this. And again, I'll keep the determinant form here. So in essence, what we're doing here is that we are saying in the first determinant I have in general n terms. Here I also have n terms, and in fact n faculty terms if n is the number of electrons, and there's n faculty terms here and n faculty terms over here also. And then I would have a 1 divided by n faculty in general. But if I just keep one particular term from the first determinant, then this term will be combined with any other term over here. And what I get is the same irrespective of what particular term I choose from the first Slater determinant. So this means I can just pick one of those terms here and then multiply everything by n determinant, n factorial, and that's exactly what we did here. Okay, so let's now start by looking at the A case, with f as some simple sum of two single body terms here. So in this case, when I plug in, I get an integral here, phi 1, 1, 2, 2, and then my operator. And now let me expand the determinant. I get a 1 prime 1, 2 prime 2, minus 2 prime 1, 1 prime 2. Right, so now I in fact have to distinguish between three different cases here. The first case is that the two Slater determinants we're considering are in fact perfectly identical. So that means that 1 prime is the same as 1, 2 prime is the same as 2. And then there's the second possibility, which is that one of these orbitals differ. So let me say that this second case is that precisely 2 prime is different from 2. This is just an arbitrary choice. I could have taken 1, of course. But the point is that there's exactly one difference between those two Slater determinants. And then the third possibility here is that there's more than one difference between the two Slater determinants. Now if we start by looking at the first case here, so we can now assume that these primes are gone. Then let's look at this integral here with operator 1. Here I have, when I have this factor together with this one here, I have 1 and the operator and 1. And then I have 2 times 2 here. And this integral here, of course, just gives me 1 because these single body states are normalized. So from this part with this operator and this one, I get phi 1 and then the f operator phi 1. Remember that when I don't write any arguments here, it's of course assumed that the argument is the same in all three factors. Then I have this part with this operator and then this function over here. So now if I again look at the 2 integral here, I have phi 2, and then over here I have phi 1. And these are orthogonal, so when I do the 2 integration, this part times this part, that will give me 0. So then let's look at the 2 terms following from this operator. Here I have phi 1, and then this operator which does nothing to electron 1, and then this thing here. So in this case, phi 1 squared integrates to 1, and then I have 2, and then the operator and 2. I get 2 F2, and then there's the final term resulting from this one over here, which again will be 0 because in this case I have phi 1 times phi 2 integrated over electron 1, and that gives me 0. So that's what I get in this case. Now let's assume that phi 2 prime is actually different from phi 2. So it might be that phi 2 prime is actually phi 3 or 5 or something different from 2, so something which is orthogonal to 2. Now if I look at this first term again, then here I get phi 1 times phi 1, and then phi 2, I have phi 1 with the operator f here, and then phi 1. But then I have 2 against 2 prime. And now we assume that they're different, so this term will actually vanish because they are orthogonal. And of course, again, this term with this part here will also vanish. Same as before, orthogonality between the states 1 and 2 prime. Remember that we don't have any accidental identities here. 2 prime is definitely different from 1. 2 prime must be 1 which was not present in the phi determinant here. But then, so I get nothing from this part here. Then I have the second operator. So the first term will be this one with this one, that the one integral gives me 1. But then I have 2 and the f operator and 2 prime. And that is not necessarily 0 because 2 and 2 prime are orthogonal. But once I have the operator in between, that can sort of cure the orthogonality, because once the f operator here has acted on 2 prime, this will be turned into a different state, and those states are not necessarily orthogonal anymore. So I will get something like 2 f operator and 2 prime. Right. So let me repeat this. The point is that 2 and 2 prime are orthogonal. So the integral between those two states will be 0. But once the operator is in between here, it will act on this state, and this new state is not necessarily orthogonal to 2. So that's why this integral might survive. Of course, the one integral here still gives me unity. And then there's the final term, this operator, this term against this term, and that again will be 0 because 1 and 2 prime here are orthogonal. So this is the only term I get. And then you can easily see that in this final case here, I will always get 0 because, again, I have operators here that will save the orthogonality for a term like this. But if both 1 and 1 prime are orthogonal and 2 and 2 prime are orthogonal, then a single body operator cannot save both orthogonalities. Let's, for instance, if we look at the first term here, then I have 1 and then the operator and 1 prime, so that integral by itself is not 0, but then I have 2 against 2 prime, and that is 0 definitely. And if I take the other operator, then 2 and the operator and 2 prime, this integral is not 0, but then I have 1 against 1 prime, and that integral is 0. So a single body operator can only save one orthogonality. So if there are more than one differences, so this means 2 differences in our case, due to orthogonality, I will always get 0. So that's what happens in the A case. Let's then do the B case. There's not a whole lot we can say apart from introducing some notation. So what I will get here in general for an operator like this let me go back here, is that I will get one factor here when I have this term, and then that part of the determinant. So that will be something I will write in this form: 1 prime, 2 prime, and then I have the other term, what I get from this, the cross term in the determinant, with a minus. So I get a minus 1, 2, and then my operator, and then 2 prime, 1 prime. So I have to write these in the opposite order because I now have introduced this shorthand notation: phi I, phi B, and some two-body operator, phi C and phi D, which is meant to mean that I take phi A with one particular argument, let's call this 1, and I have the B with a different argument, and then my operator. And then the C state here, by convention, will have the same argument as the A state. So the first one here will have the same argument as the first one over here. And similarly, the B state will have the same argument as the D state. So I also get a D with argument 2. So that is my convention for the notation. So that's why in this term over here I will have to interchange the order of the two, because in this part over here it's the state 2 prime which appears with argument 1. And this is an example of what we generally call an exchange term. And the reason for this notation is pretty clear, because what I simply did here was that I exchanged 1 and 2. Either you can think of it as the interchange between the states here, or, and that's probably more convenient, you can think of it as exchanging electrons 1 and 2. And mathematically this implies that we should write these in the opposite order with this notation. So that's what I get in that particular case. So now we should try, as I promised, to generalize this to the n-electron case. So I will start by looking again at the A case. So let's remind ourselves what happened with only 2 electrons. In this case here, if the two states were actually completely identical, I got the sum here. Then in the case that there is precisely one difference between those two these two states, I only got that particular matrix element. And the reason again was that I needed to sandwich the operator f between those two states, because otherwise that integral would always be 0. Right? So if I have orthogonal states here, then I need to put the operator in between to get anything non-zero. And then finally, if there were more than one difference between the two Slater determinants, I would always get 0, because a single body operator could only cure one orthogonality. So then you can probably easily see that in this case, so I have the idea here is that I have an operator which is a sum of identical single body operators. So my matrix element here again splits into 3 cases. There's the one in which there are no differences. Then there's one case where there's precisely one difference. So I say that phi k prime is different from phi k precisely, or we could also say only. And then there is the final case with more than one difference again. And in the first case, what we simply get here is a sum of all single body terms. So here I get a K, F, K. And this, of course, simply generalizes what we did here. The point is that as long as the two Slater determinants are completely identical, then I will always get a term from each of those terms in the operator, because there are no orthogonalities, so this term, the first one here, will always survive. So that simply is going to give me a term for each of those states. Then if we look at this case, what we get is that only one term survives. Because as long as K and K prime are orthogonal, again, I need the operator between those two states in order to make this factor non-zero. If the operator is not between K and K prime, then this factor will kill the contribution. So there's only one term surviving in that particular case. F must be between K and K prime. And then, of course, down here I will still get 0, because if I have a sum of one-body operators, then I can not cure more than one orthogonality. So if there are more than one, I will always get 0. So that's the generalization to an arbitrary number of electrons if I have this sum of one-body operators. So let's proceed to the B case. So now my F operator is a sum over all pairs of some two-body operator. So let's again look at what happened here. Well, if there were only two electrons, we got this particular term here with the 1' and 2' in the one-hand side. Now we're looking at a more general case. There are n electrons, so I have a number of pairs here in my operator. So I need to distinguish between, in fact, 4 cases. So there's the first case in which the two Slater determinants are precisely identical. Then there's the second case, which is similar to before. It's the one in which K prime is different from K. And this again should be understood in the sense that only K prime is different from K. All the other entries are the same. Then I have a third possibility here, which means that I should consider K prime different from K and L prime different from L. So now there are two orthogonalities, or two differences between my two Slater determinants, and then obviously there's a fourth possibility, and it's that I have more than two differences, right? So to recap here, either I have 0 differences between the two Slater determinants, or I might have precisely one difference, or I might have precisely 2 differences between my Slater determinants, and then finally I might have more than 2 differences. So let's start from the bottom here. This is a two-body operator, and in analogy with what we did before, this might cure 2 orthogonalities. So again, what we're doing here is that we are integrating psi against psi prime. And that leads to a number of products between single body states. And if I ever get one state against an orthogonal one without an operator, the corresponding contribution will always vanish. So if there are more than two orthogonalities and I only have two-body operators here, then this third option here must be 0, because this two-body operator can only cure two orthogonalities. And then it of course follows that in that particular case here, where I have precisely two orthogonalities, this will be the only term which can survive. So I will get K, L, and G, K prime, L prime, and then the exchange term, K, L, G, L prime, K prime. So this is the same precisely as we had before, but now the point is that if I have these two states different, then they must both be acted upon by the operator G here, so I only have this particular term non-zero. Any other terms of the many that I have when I expand both Slater determinants will be 0, because K and K prime are orthogonal, L and L prime are orthogonal, so if they're not acted upon by the operator, I must get 0. So there's only one term, including its exchange contribution, which is non-vanishing. Okay, then we can step up one here in one place in this scheme, because if K prime is different from K, obviously I need the operator to act on K prime in order to get something which is non-zero. On the other hand, L prime and L are the same in this case. So the L prime, or L in general here, can be anything. Now this means that I am allowed here in this case to sum over L. I get a K, L, G, K prime must be in my term, and then the L, and then again the corresponding exchange term. It's an L, and here's the K prime. So again, let me recap here. The point is that now L prime and L are the same in this term, so they're both called L. And that L can of course be anything. So I am allowed to sum here. Yeah, of course, in principle, L should be different from K, right? But otherwise, I am allowed to sum over everything here. So we might say L different from K. But otherwise, I can sum over all of them. So there's the generalization of this term to the case where there is, in fact, only one difference between the two Slater determinants. So this means that I must have this particular value inside my term in order for G here to cure the orthogonality. And then, of course, it follows easily that in this case, where they are perfectly identical, I don't need to restrict the values of L and K to anything particular. So that means I will, in this case, simply get all pairs K, L, G, K, L minus K, L, G, L, K. Right. In this case, all pairs, since I am only summing over pairs, all pairs should give me a contribution, and there are no restrictions because there are no orthogonalities. So it doesn't matter which states are acted upon by the operator and which are not, because I don't get any orthogonalities. So that is the generalization to an arbitrary number of electrons for my two cases, the A and B cases. So now what we're going to do is apply this to something which is of particular importance, and that of course is the Hamiltonian. The Hamiltonian is a sum of single body terms and then two body terms. The two body terms are of this particular form. It's simply the repulsion between electrons I and J. And that of course complicates things, but there is one simplification still, because this is not a true operator. In fact, this is just a function. So what it means is that whenever we encounter this operator, this is of course my G operator, whenever we encounter this G, we don't have to worry about the order of factors. Since this is not an actual operator, we can just shuffle factors inside integrals as we wish. There's no need to pay any attention to any order here. Again, since this is not actually an operator, it's just a function. So let's consider the simplest case, the fact that the case in which we're just considering two identical Slater determinants. And this is the one we'll be needing in most cases. So this is what I need if I am just looking at a single Slater determinant and I'm computing the expectation value for that particular state. So I use this Hamiltonian and identical Slater determinants to the left and right. And now it's a simple matter to use the rules we just derived. I have a single body contribution. Again, so let me write this, that my Slater determinants are of the form phi 1, phi 2, all the way up to some phi n. So here I simply get single body contributions which are like this, sum for each of them, sum with a contribution for each of them. And then, since these are identical, then I get from the two body terms the same as we just derived here. Get an I, J, 1R over R, let me call them call it 1, 2, I, J, and then the exchange term here, I, J, 1 over R, 1, 2, J, I. There you go. So this is the general result for the expectation value of the energy. The convention here, of course, is that the argument in the first factor, the first function here, should be R1, and the argument here should be R2, R1, 2, then being simply the distance between electron 1 and electron 2. So this is the general result, but we can actually simplify it somewhat. First, let me introduce some additional notation. This integral here, this number, will be called h sub I, and then I'll give it a prime, and in a moment I'll explain the meaning of this prime. This integral here will be j sub ij prime, and then this one will be k ij prime. So let me explain this notation. The first part is simple. This is just a single electron contribution. Then there's this integral here. This is what we will call our Coulomb integral. And I'll show you in a moment why this is the natural name. And then there's this one over here where I and j are interchanged or exchanged, and this of course is an exchange integral. So my expectation value consists of single electron contributions, Coulomb integrals, and exchange integrals. And one very important fact here is that there's a minus in front of all the exchange interactions. And this is not terribly obvious, but in fact exchange integrals are always non-negative. They might be zero, but they're never negative. So this means that this is actually, including the minus sign, it's actually a negative contribution, which will be important later. And in the same fashion, the Coulomb integrals are actually positive. So with this notation here, I can simplify the expression for my energy. And now let me explain the meaning of the primes here. Because what they mean is that when we evaluate these integrals, we still haven't done the spin integrations. Here, remember that this implies, in fact, a fourfold integral, 3 spatial ones and then 1 spin integration. Here, this implies an 8-fold integration, 6 spatial ones and 2 spin integrals, and the same here. So the primes given to these integrals means that we still have to perform the spin integrations. So the primes now have a completely different meaning, different to what we used the primes for just before. But in fact, it's pretty easy to do those spin integrations, and that's why it's convenient. So let's look at hi prime. Again, this is phi I, h phi I integrated over spatial and spin degrees of freedom. And remember now that spin integration actually simply means that you look at the two states in this case and then consider whether they have the same spin or not. If they have the same spin, spin integration gives you 1. If not, spin integration gives you 0. Spin states are orthogonal. But in this case, I of course will always get 1 because I have identical states to the left and right. So obviously this and this state must have the same spin state, and spin integration will always give me 1. So I can simply say that this would be the same as hi without a prime. So without prime, of course, means after spin integration. So this is just to point out that for those single electron terms, spin integration always can simply be ignored. You just focus on the spatial integrations because spin integration must give you 1. And in fact, the same thing goes for the Coulomb integrals. Let me write what this in fact means. It's an 8-fold integral. So I have phi I with an argument, let's call it x1 squared, and I have phi j with an argument x2 squared over r12, and then d4x1, d4x2. So here I've explicitly implied that I should do spin integrations for electron 1 and electron 2. But again, what I find here is that spin integrations will always give me 1 because I have phi 1 against itself, and of course so I have phi I against itself, and that of course gives me a spin integral of 1. And here I have phi j against itself with one particular argument. So again, that must give me a 1. So for the Coulomb integrals, I will simply skip the primes, again implying that we don't need to worry about spins for the Coulomb integrations. They will always lead to a factor of 1. So we just focus on the 6 remaining spatial integrations. But then I have the exchange terms, and they are slightly more complicated, because then in this case I have phi I conjugate with argument x1, and then phi j with argument x1. And for the second term I have phi j conjugate argument x2, phi I argument x2. Everything here divided by r12 and then my 8 integrals. And now you see that this is a different situation, because now I have phi I against phi j with the same argument, and there's no guarantee that the spin parts of I and j are the same. And it's in fact the same over here. It's I against j with one particular argument. So there's a chance that this integral will actually vanish. And what we can say is that it's whatever you would get by ignoring spin integrals times a delta of this form. Right? If the spin parts of I and j are the same, we get this factor, the spatial integrations. But if they are different, we get 0. So this is a very important physical fact. It's the point that this exchange interaction only occurs between electrons with the same spin. If the two states that we use to construct the Slater determinant have opposite spins, then there is no exchange interaction between them. Only repulsive Coulomb interaction. So you see that this will have some physical implications, because we have this negative energy, this contribution when I include this minus here, but I can only get this contribution provided that I have identical spins. So let me summarize here that the expectation value is comprised of a number of single body terms, and then there are all the interaction terms where I sum over all pairs. I have Coulomb repulsion terms for all pairs irrespective of their spin, but then I have exchange interactions whenever I encounter two states with identical spin. Otherwise, there is no exchange interaction. So now let's see how this works out in practice. So the first thing we might look at is the helium ground state. So this is a state of this form, a 1s2 configuration, one of those states having spin up and the other having spin down. So let me use my expression here. So I get the two single body terms, where again, since there's no prime here, I have already done the spin integration. So this means that it doesn't matter whether I consider the plus or minus part. Both of them will give me exactly the same, and I get simply 2 times what I might call H1s. And then I have to look at all pairs, but there's only one pair in this simple case, since there are only 2 electrons. And the 2 states here have opposite spin, so there are no exchange terms in this case. There's only the Coulomb term here, J 1s. 1s. So just to clarify here, let me try and explain what this means. So I have this 1s state, which is just some spherical harmonic with a very simple form. It's in fact just a constant, and then some radial part here. And my H1s is simply an integral of this phi 1s state, argument r, and then my single body operator h, and then another 1s function, and then the 3 spatial integrals. And for this helium case, of course, my one body operator is the one we've seen several times by now. It's simply this. So this is the single body contribution to the energy, and since there are 2 electrons, I multiply by 2. And the Coulomb integral is then a 6-fold integral, phi 1s argument r1 squared, phi 1s argument r2 squared, divided by their distance, and 6 spatial integrations. You might actually recall that this is exactly what we have been evaluating before when we evaluated the expectation value for the helium ground state and used variational calculus to figure out which exponential function gave us the best fit for the ground state. So this expression is precisely the same as we've seen before. But now we can also try and be a little more elaborate, because we could look at excited states. So let's look at the excited states of the form 1s, 2s. So in fact, there are 4 of them. There is 1s plus, 2s plus. In this case, they are allowed to have the same spin. And there's a 1s minus, 2s minus. And then there are 1s plus, 2s minus, and 1s minus, 2s plus. Those are the 4 possible Slater determinants I can form in this manifold here. And now we have to think back to what we did in the last lecture. Because what we figured out is that when I couple 2 electrons with only spins, so there are no orbital angular momenta in this case, there are only spins, then they will couple such that they form a singlet term and a triplet term. So we had a singlet which we might call phi s, which was actually 1 over root 2 and then the 1s plus 2s minus minus the 1s minus 2s plus. That's what we found for the singlet. It was this linear combination of Slater determinants. And then we had the 3 terms comprising the triplet. So there is the 1s plus 2s plus. This was, if let's recall the notation, this was the 0, 0 eigenstate of the total spin. This was the 1, 1. And we had the 1s minus, 2s minus. This was the 1 minus 1. And then we had the linear combination here, 1s plus, 2s minus, plus 1s minus 2s plus. And this was the 1, 0. So those 3 states here form a triplet, and this single one here is the singlet state on its own. And again, on physical grounds, we expect the energies of those 3 states here to be the same, but possibly different from what we get in the singlet case. So now we would like to use our rules to compute the expectation values for these states. So we could start with the triplet, because in this case there are simple options, because I can look at either this or this one. These are simple because they consist of just a single Slater determinant. So let me go back to my rules here. I should sum the single body terms and then sum of all pairs of Coulomb and exchange interactions. So here, if I consider, for instance, this one or this one, doesn't matter, they of course give me exactly the same. I get a triplet energy here, which is then this H1s plus H2s, so that's the single body contributions from the 1s and 2s states. And then I have a single Coulomb interaction, because I have, again, just one pair, a 1s against the 2s, so I get a single Coulomb term. But now in this case, I also get an exchange term, because in both this and this case, there are identical spins, so I get an exchange interaction term. So that's what I get here. Now, here we then have to look at those more complicated states. And what we would like to show is that this state, when we use this state, I will actually get the same as we have here. And then when I use this state, I should probably get something different. So let me use the notation phi plus minus, just to have both of them as this one plus or minus this one. And what I'm trying to calculate are these expectation values. So first of all, I get 1/2 from this prefactor. Then I have this factor with itself. So I have the 1s plus 2s minus, and the Hamiltonian 1s plus 2s minus. And then I have this one with itself. It's the same, except that plus and minus are interchanged. And you will easily recognize that this has no effect. Whether what I call up or down does not matter. So this term with itself will just add to a factor of 2. Then I have this factor against this factor. So that term will enter with a plus or a minus. So I have 1s plus 2s minus, and the Hamiltonian 1s minus 2s plus here. And then the final term, this term against this term, this one on the left hand side, this one on the right hand side. But again, this is just the same as this, except for plus and minus is exchanged. So this also simply implies a factor of 2. So you see that we have something new here, which I might expand. I have the first kind of term here. And this is the same type as we already considered, because in this case, the Slater determinants to the left and the right are the same. But then I have these additional terms here, and they are of a different type. Because in this case, there are differences between left and right Slater determinants, because the spins are flipped. Right. Here I have 1s plus against 1s minus, and here 2s minus against 2s plus. So this is a new kind of term. The first one here is as simple as what we calculated already. So again, I turn to my recipe. I get H1s and then H2s from the single body terms. I get Coulomb interaction, 1s, 2s. And in this case, I don't get an exchange interaction because the spins are different. I have a plus against a minus. But then I have this term over here, which enters with a plus or a minus. And now I have to think a little harder, because again here I have different Slater determinants. And I have to count the number of differences. And we see that the number of differences is in fact 2. Because this state is different from this one is different from this one. So now I have to go all the way back to my general expressions here, because my Hamiltonian, which is sandwiched here, has single body terms and 2 electron terms. But the single body terms will not contribute, because I'm considering Slater determinants with 2 differences. And if there are more than one difference, I do get 0. So there is no single body terms from this part, only two body terms. So let's look at what we had for the two body terms. Well, this was the case where there are precisely two differences, and we get the Coulomb, or the direct part, and then this exchange part. So the Coulomb part is, well, let me write it here. I have a 1s plus and a 2s minus, and then my operator, and this one over here, 1s minus, 2s plus, and then the exchanged part, let me write it down here, 1s plus, 2s minus, operator, and then I exchange terms here. Like this. And now we have to consider these integrals here, because obviously here spin integrations are not yet performed. And the operator itself does not involve spin again. So spin integrations are very simple. We simply have to consider the states with same argument and figure out whether they have the same spin or opposite spin. And in the first case, clearly spins are opposite. Here I have a 1s state with spin up and one particular argument, let's call it 1. And here I have the 1s state with spin down and the same argument. So when I do the spin integral for that coordinate, or in fact for the other coordinate, I will get 0. So this term here, in fact, vanishes, and we could say that this is due to spin integration. And then there's this term here, and now this is a term which does not vanish, because once I interchange the two terms here on the right hand side, spins match. Now I get a plus against a plus and a minus against a minus. Of course, here I have orthogonal spatial orbitals. I have a 1s against a 2s, but my operator here will lift this orthogonality. Once the operator is sandwiched between a 1s and a 2s state, integration does not give me 0, because this also involves the spatial coordinates. And this integral, in fact, is precisely the exchange integral. This is precisely k 1s 2s. It's where I interchange the spatial parts here. So I have a 1s and a 2s with one argument, and then I have a 2s times a 1s with another argument, and then all of this times my operator and integrated over my 6 spatial and spatial coordinates, and that gives me the exchange interaction. So now we can recap things here, because I had the Coulomb integral, and then I had plus minus the exchange interaction. So in fact what I end up getting is H1s, H2s, J1s, 2s, and then minus plus K1s, 2s. And this I can compare to what I had here already. And remember that the upper sign here, the plus, the upper sign here is what goes with the triplet. And you see that things really do match up, because the upper sign is a minus in the energy expression, and that's exactly what we had already. So if I consider the phi plus state here and use this to evaluate the expectation value, I get this result, which is precisely what I should get. So what we've shown here is that this more complicated term, or part of the triplet term, in fact gives me the same energy as those two states here. On the other hand, the singlet, the lower sign here, has a different energy. So I can finalize here by summarizing what we find for the helium atom here. So first of all, there's the ground state. So that is the 1s2 configuration, Slater determinants, 1s plus, 1s minus, and it has an energy somewhere down here. And then there's the lowest excited state, and that's in fact the triplet. And then there's a slightly higher excited state, which is the singlet. So these are the excited states. And here the energy I get for the ground state, let's call it, here is 2H1S and then Coulomb 1S, sorry. And then I have the triplet energy 1s, 2s, 1s, sorry, again, 1s, 2s, minus k, 1s, 2s, and then I have the singlet h1s, 2s, 1s, 2s, plus 1s, 2s here. Right. I have this sign difference here, minus for the triplet, plus for the singlet. And again, you can show using actually the Fourier transform that these exchange integrals themselves are always positive. So that is what we get. And in terms of numbers, this split here, if I go between the ground state and the midpoint here, this is roughly 20 eV, and this split here is roughly 2 eV. So this is how things go for the helium atom. You see that the lowest of the excited states is actually the triplet. And the physical reason why this happens is that in the triplet I have identical spins, which allows me to use the exchange interaction. Exchange interaction because it has a minus. Again, maybe I should go all the way back here. You see that in this term there's always the minus. The exchange interaction will lower the energy. So all things being equal, we should try and maximize the triplet amount. So this means maximizing the number of identical spins. That is favorable, and you can see that in this case that it lowers the energy by roughly 2 eV compared to the identical situation with opposite spins. But of course you have to understand this in the right sense, because obviously in the ground state we do not have parallel spins, because there's also a price to pay if you have parallel spins, and the price is that the spatial parts must then obviously be different, and that comes with a huge price. In fact, the price here, you see, apart from small differences due to these terms here, the price here is that we replace 2H1S by H1S plus H2S. So this difference here is roughly H2S minus H1S. So that is the price you have to pay by replacing a 1s spatial state by a 2s spatial state. That's a price of the order of 20 EVs. But then once you have replaced the 1s state by a 2s state, then you are free to choose the spin of this 2s state. And then it's favorable for the 2s state to have the same spin as the 1s state, because that gives you the negative exchange interaction. And that's why the triplet is the lowest among the excited states. But obviously the ground state is in fact a singlet. And we can then also return all the way to the carbon atom we looked at last time. In this case, in fact, we had a very complicated calculation of the various terms. Let me see if I can find them here. There you are. These were the 3 terms we calculated for the carbon atom. We had a 1D term with 5 members, we had a 3p term with 9 members, and then we had a 1s term. So we have 3 distinct terms in the among these candidates for the carbon ground state. You remember that we're talking here about candidates for the ground state. These are all configurations where the 6 electrons are in a 1s2, 2s2, and 2p2 configuration. And now we can actually understand why it's this triplet that is the actual ground state of the carbon atom. It's because in this case we have the maximal spin. This is a triplet, whereas these other terms are singlets. And this means that in this configuration, where the 2p orbitals are chosen such that they have parallel spins, in this configuration we actually lower the energy. You might recall that this term consists, for instance, of a configuration such as this one. If you don't remember, maybe you should go back and review this lecture. But this building block here is part of the this term, this triplet. And obviously here you see that we have parallel spins for the 2p electrons. And that is in fact favorable. And when you look at the numbers, you'll find that this state is lower than this one by something on the order of a few eV. So this is the actual ground state of a carbon atom. And the explanation again is that we need parallel spins to utilize the exchange interaction. So let me finish here.